The Huckel's molecular orbital theory, part 2, is the subject of this discussion. I'm your instructor, Saurabh Bhaktivinoda. In the earlier video, we have seen that a secular determinant of order n into n can be constructed, which is apparently shown to have the form of the kind h11 minus es11 h12 minus es12 dash this goes to hin minus esin, followed by number of terms that are there through the secular equations, and a determinant of order n by n has been constructed using the method. In all this discussion, it was assumed that an electron in a particular orbital may be assigned a definite energy. Only two non-identical electrons may occupy a given orbital, and the forces involved in chemical bonding or binding are electrostatic in nature. Well, when we have developed this idea using a small equations C1 psi1 is equal to C2 psi2 for, say, the simplest case of hydrogen molecule ion, we started with the Schrodinger wave equation H psi is equal to E psi, and multiplying by psi on either side and evaluating its value for energy, we have reached to certain conclusions, and this is before us that we have got a secular determinant of order n into n. If we have a conjugated system of, say, 3 pi electrons, then we'll have a determinant of 3 into 3. If we have a conjugated system of 4 electrons, then we'll have an order 4 into 4. If we have a 6 electron system like benzene, then we can have a 6 by 6 determinant to solve for its resonance energy. Now, to proceed further, let us recall the fact that the integrals HII or HIJ type of integrals are known to be a very specific kind of integrals, and they are given certain abbreviations by Huckel. So when we assume that all the integrals they are of HIJ type, they are known as the resonance or exchange integrals when I is not equal to j, and otherwise the all HII type of integrals are assumed to have the value of alpha. So H11, H22, H33 type of integrals are known as Coulomb integrals, whereas the Hij type of integrals are known as the exchange integrals or resonance integrals. And for that, the Huckel's approximation was of the type that all integrals of type Hij is equal to alpha provided I is equal to j. They are equal to beta if I is not equal to j, and I and j are interacting orbitals in a cyclic or an open system, and Hij is assumed to be equal to 0 when I is not equal to j and I and j are not connected atoms, so there is no direct interaction between I and jth atomic orbitals, pi orbitals. So this is the case. Similarly, when you talk about the Sij type of integrals, which are known to be the overlap integrals, it was assumed that all integrals of the type phi I, phi j d2 is equal to 1 if I is equal to j, or otherwise all such integrals are given the value of 0 when the I is not equal to j. So you know that the d2 is the space element or the volume element that we are talking about integration into the entire space, and the Sij is representing the overlap between the two atomic orbitals. So in this approximation, it is believed that either there is a complete overlap that gives the probability value of 1, or there is no overlap at all that gives the value of 0. Because they were developed by Huckel, these are known as Huckel's approximations, and they are very good in estimating the resonance energies of cyclic or non-cyclic, the conjugated systems. So the Huckel's theory is very important in finding the resonance energies of various systems. As far as the secular determinant is concerned, with the light of new approximations, that is Hij are equal to alpha if I is equal to j, there is equal to beta if I is not equal to j, all the diagonal elements are turning to alpha minus e, because you can see that this H11 is alpha and S11 would be 1. So if this is 1, this is energy. So what is left is alpha minus E. So alpha minus E are running diagonally while beta terms are running off diagonally. All the beta terms are running off diagonal. However, here in this view, we have not shown that which are the interacting orbitals or which are not interacting orbitals. This is just an overview or the style in which we are going to solve such determinants. And in light of this, it has been assumed that if we solve these equations, they are certain polynomial kind of equations, and when they are solved for values of energy, then ultimately in terms of alpha and beta, we have something like alpha minus E is equal to minus mjb beta, or plus minus value when j can have certain values of 1, 2, 3, etc. So there are two real values, there are plus values or minus values. So energy can be represented as a series of energies above and below the energy zero in the scale of alpha. And because alpha and beta are both inherently negative, therefore the alpha plus mj beta is said to have a negative value altogether, and this forms a stable molecular orbital. However, alpha minus beta is assigned to we have an antibonding molecular orbital, whereas those with m is equal to 0, that is only in terms of alpha, they are assigned as the non-bonding molecular orbitals. So the entire scenario is something like this. In terms of energy scale of alpha, bonding MO, bonding molecular orbitals are of the lowest energy, non-bonding have the intermediate energies, and anti-bonding have the highest energy in terms of energy scale of alpha. So that is the energy in terms of M alpha, in terms of alpha only, and M minus alpha. This is the order in which the electrons, according to the Hund's rule, would be filled. As you know that in each order only 2 electrons can be occupied. So this is a general case so far we have discussed. Now we'll be talking about the specific case in the next videos. Thank you for watching this video. See you in the next phase.